Hi everyone. Today we're going to talk about changing angular momentum of a system and what that looks like. So first, let's talk about how you can change linear momentum of an object. So when we're talking linear momentum, right, we're talking about right, P equals mv. Okay? And to change linear momentum, we were talking about impulse, right? Impulse is the integral of f dt, right? Which is the change in momentum. You can also show that as a summation of external force equals the derivative of momentum with respect to time, which is saying that momentum will change over some time period, right? So that's how we can change momentum of an object in the linear world, right? Momentum is conserved in collisions within a system, but as soon as an external force is acted on an object, that's going to change its momentum. For example, if we were to break this down, dp over dt, you would have d times mv over dt, which would give you ma because dv dt is a, right? So if there is acceleration of an object, you are changing its linear momentum, and that's no longer conserved. All right, now what happens in the rotational world? So in the rotational world, right, we've been saying for a while that force has this relationship with torque in the rotational world, right? So when we think rotational force, we're thinking torque. So what does torque actually have to do with changing momentum? So let's look at this. I'm going to go down below, right, real quick. So we have summation of torque equals radius cross with this summation of force, right? Now we can say that the summation of force can equal dp dt, like we just established. So we have summation of torque equals r cross with dp over dt. Okay? Now we can actually distribute that, right? So we can say that the derivative of r cross p divided by dt is the summation of torque, right? Now before I make that change, I do want to note that this means that radius, and if we break down momentum, that is mass and velocity, okay, they all can change with time. They all can change with time by a result of torque. Right? So torque can cause a change in radius, a change in mass, or a change in momentum by using this definition. Now we also want to use the definition that r cross with p equals angular momentum, right? So that means that the summation of torque, oops, back to there, would result in a change in angular momentum. So where force results in a change in linear momentum, torque will result in a change of angular momentum. Excuse me. Now, number 4 is the last part here. I do want to draw your attention over to this picture real quick. This is a similar image we have used to demonstrate conservation of energy, right? But when angular momentum is conserved within a system boundary, okay, then you've got conservation. But the thing that can add or take away the angular momentum of a system is external torque, right? So, and then it even says the rate of change in the angular momentum of the non-isolated system is equal to the net external torque of the system. So external torque can change by adding or taking away angular momentum. Now, then we have this statement. So blank is the angular equivalent of blank in the rotational world. Okay? So the major answer I want to show is that torque is the angular equivalent of force in the rotational world. However, I have had students mention this one, which I think is a little bit more obvious, but it is true in the discussion we're having. You can also say that angular momentum is the angular equivalent of momentum in the rotational world. Okay. Torque and force are kind of the point I'm trying to make, but angular momentum and momentum also serve that purpose, right? Now, this is a top 10 problem from when our previous teacher, Mr. Askey, was teaching this class. Mr. Askey clings to a vertical ladder and directs the nozzle of a hose horizontally to save the burning science building. The hose passes between Mr. Askey's feet and rests on the ground 1.3 meters below the nozzle. The rate of water flow is 6.31 kilograms per second, and the speed of the water at the nozzle is 12.5 meters per second. So let's draw this first. So we have this hose spraying water. Okay, that water comes out at, what was it, 6.31 kilograms per second. That's the water flow, right? And then the velocity was 12.5 meters per second, right? So it then goes on to ask us, okay, we drew it first. Now it asks, what torque and force must Askey apply to keep from falling off the ladder, right? Because this is actually a torque problem here. We can see here that it's going to try and pivot about this axis down at the bottom, right? It wants to rotate in that direction, right? As a hose pushes water uncontrolled, it will just go backwards, and we're saying that it would rotate about the axis 1.3 meters below the nozzle. Now, if we want to find torque and force, okay, I'm going to start with force, and then we'll do torque, but you can actually do this the other way as well. So I'll show you that demonstration as well. So force, okay, force is dP over dt. Okay, here, this water flow is dm dt. Okay, that is a change in mass over time, and this is a constant velocity that we can use for this. So if we split up dp dt, that is dmv divided by dt, which can be shown as dm dt times the velocity, right? So if we do that math, we simply have 6.31 kilograms per second times 12.5 meters per second. So if you do that math, you should get something around 78.9 newtons, okay? Because you get a kilogram meter per second squared, which is a newton, right? So there is your force. Now, if you want to find torque, torque is R cross F. But if we know that R is perpendicular to F in vector terms, then torque can just equal R times F. Okay, whoops, not parentheses. Absolute value. There we go. So if we look over here, this would be our radius. And our radius vector would, I guess I shouldn't put that arrow. That's not technically correct, right? But our radius would be along the vertical. The force is along the horizontal. It actually says that he is directing the nozzle of a hose horizontally. So that is said. And then we know the hose is going down vertically. So with this assumption here, we can just multiply the radius by the force. So we already have the force. That is 78.9 newtons that we just found. And then we know the radius would be 1.3 meters. So the torque in Newton meters would be approximately 103 Newton meters. Okay. So that's how you can find the torque and force exerted by Askey to make sure that this is all balanced. Now, another way to do this is to show that torque is dL over dt, which would be dmvr over dt. We know V and R are constant. So this would be dm over dt times vr. And then we know that force is torque divided by radius with that perpendicular assumption that we made. So then this would be your 103 divided by 1.3 to get your 78.9. So that is another way that you could do that. I just chose to do that arbitrarily, force first, torque second. Okay, both of those are going to give you approximately the same answers. All right, now let's talk about connections between angular momentum, torque, and acceleration. This is actually going to lead to a new method of solving physics problems, but we're going to save practicing that method for our next video. So given we have L equals I omega. If we take the derivative with respect to t, we get that dl over dt equals di omega over dt. We haven't encountered any time where the moment of inertia of an object was changed by torque. So we will say that this is I times d omega over dt, which leads to, you know what? That's the next step. I d omega over dt. Then the next step says sub 4 d omega over dt. So you get dl over dt equals I alpha. Then get torque to sub 4 alpha. Kind of a weird way to say that, but that's just establishing that torque is I alpha is dl over dt. Okay. This is our dl dt torque alpha, or the L torque alpha, LTA, however you want to say it. We call it a triangle or a circle. Okay, so you've got dl over dt, then you've got I alpha on this end, and then you've got torque on this end. And if you have one, you can directly solve for the other using their relationships that they have in common. Okay? So you got to keep in mind that torque also equals R cross F, and dl dt equals really the derivative of mvr over dt. So if you have a change in mass, change in velocity, change in radius, you can use dl dt. If you've got radius and force, you can use torque. And then obviously if you have alpha or moment of inertia, you could use I alpha. And then you can solve back and forth using this triangle. Now we're going to get more practice of this using our next video to account for time. But this is going to be an important way to solve some more complex problems that we're going to approach.